Hello dear student, myself Prof. K. Today we learn next part of electrostatics. First part we can discuss what is a statement of a Gauss theorem or Gauss law, and then we can discuss three application of a Gauss law. In the second parts of electrostatics we can discuss some important concept. First one, electric potential and potential energy. Then we can discuss what is meant by electrostatic potential energy. Then we can derive expression for potential energy, and another one we can discuss concept of a potential, and next one is a relation between electric field and electrical potential, and last turn we can discuss zero potential. These all terms we can discuss sequentially one by one. Uh, in this video, we firstly discuss what is by electric potential, and then we can discuss potential energy. Let's talk about what is by electric potential. Let us see first potential energy. We know that like charges repel and unlike charges attract each other. A charge exerts force on any other charge in its vicinity. Some work is always done to move a charge in the presence of another charge. Thus, potential energy arises from any collection of charges. Firstly, we can discuss what is meant by electrostatic potential energy. What do you mean by electrostatic potential energy? Definition here. What is meant by potential energy? The electrostatic potential energy of a system of a point charges is defined as the work required to assemble the system of charge by bringing them from infinity to their presence location. I repeat again definition. The electrostatic potential energy of a system of a point charges is defined as the work required to assemble the system of charges by bringing them from infinity to their presence of location. Work done, that is electric potential energy against force, we can given here du is equal to F into dr. Here du be the electric potential energy when the charge is displaced from dr, and F be the force exerted on charge. Then we derive expression for potential energy. Expression for potential energy. See this diagram. Consider a charge q. Consider a charge plus q at point O. Let a small charge small plus small q0 be brought from point A and from point A to B. See here, this is a plus small q0 be the brought from point A to from point A to from point B, A to from point B at respective distance. Suppose at A distance we consider small r1, we consider distance small r1 and r2 from point O against the force on it. Suppose this force is F suffix E. Uh, this is a uh, force plus Q displaced by dr toward the charge plus Q. Then work done against the force F suffix E is displacing charge Q0 through the displacement dr. Then we can write here work done against the force F suffix E is displacing charge Q0, small q0, through the displacement we consider dr is du is equal to minus fe into dr. Consider equation 1. Here this negative sign indicates that displacement dr and force F suffix e are in opposite direction. Then integrating above equation, first with limit we can take limit r1 and r2, we get change in potential energy. This potential energy we can write here potential energy delta u is equal to integration changes from r1 to r2 du is equal to minus integration changes r1 r2 fe into dr. Consider equation second here. By Coulomb's law, force between q and q0 is the electro. By using Coulomb's law we can write this F suffix e is equal to minus 1 upon 4 pi epsilon naught into q0 upon r square. Consider equation third. This is a force in Coulomb's law, force between q and q0. F suffix e is equal to minus 1 upon 4 pi epsilon naught into q0 upon r square. Then put equation third, this equation third, put equation third in equation seconds, we can write this du is equal to minus integration changes from r1 to r2 1 upon 4 pi epsilon naught into q0 upon r square into dr. Then we can write this du is equal to minus r1 minus integration changes r1 r2 upon r1 integration changes du is equal to minus integration changes r1 r2 1 upon 4 pi epsilon naught into q1 into q0 upon r square into dr. Okay, here we can write du is equal to minus q into q0 upon 4 pi epsilon naught integration changes r1 r2 into we can write this term 1 upon r square 1 upon r square. Then we can write in this way r raised to minus 2 here. Okay, du is equal to minus q into q0 upon 4 pi epsilon naught integration changes r1 r2 because uh, q0 and 4 pi epsilon naught is a constant term. Then we can write this term in outside the integration. then du is equal to minus q into q0 upon 4 pi epsilon naught, then integration changes r1 r2 r raised to minus 2 into dr. Take a rule of integration. Du is equal to minus q into q0 upon 4 pi epsilon naught into r raised to minus 2 plus 1 upon minus 2 plus 1. Integration changes r2, upper limits r2 and lower limit r1. Then du is equal to minus q into q0 upon 4 pi epsilon naught. We can write minus 2 plus 1, this become minus 1, and minus 2 plus 1 minus 1. We can write du is equal to minus q upon q0 upon 4 pi epsilon naught into r raised to minus 1 upon minus 1. Integration changes from r to r1. Then here r2 is the upper limits and r1 is a lower limits. Then we can write du is equal to minus q into q0 upon 4 pi epsilon naught into minus 1 upon r. This become upper limit r2 and lower limits r1. Then we can write this or put these upper limits and lower limits. We can write this minus minus become plus. Du is equal to plus q into q0 upon 4 pi epsilon naught 1 upon r2 1 upon r2 minus 1 upon r1. Consider equation number 4. This is a required equation, uh, for a expression for electrostatic potential energy. Some question asked on this topic: derive an expression for electrostatic potential energy. Sometime we discuss here some question. Change in electrostatic potential energy depend upon endpoints and it's independent of actual part taken by charges. Verify change in electrostatic potential energy depend upon the endpoints and is independent of actual path by taken by charge. Then we can implies that change in electrostatic potential energy depend upon the endpoints and independent of actual part taken by the charge. Then for 1 marks question, state formula for work done against the electrostatic force while displacing charge plus q0 at a distance r1 toward the charge plus q at distance r2. Then we can write work done against electrostatic force, change in electrostatic potential energy. We can write w is equal to delta u is equal to q into q0 upon 4 pi epsilon naught into 1 upon r2 minus 1 upon r1. Okay, then another formula we can write this, another question for 1 marks. Write formula for potential energy u, system of 2 point charges q1 and q2 separated by distance smaller. Then we can derive another way. U of r is equal to q1 into q2 upon 4 pi epsilon naught into r. Basically, as electrostatic force at a r is equal to infinity, it is convenient to choose electrostatic potential energy to be 0 at infinity. Thereby equation delta u is equal to q1 into q2 upon 4 pi epsilon naughts into 1 upon r1 minus 1 upon r2 minus 1 upon r1. By using r1 is equal to infinity and r2 is equal to r, we get potential energy of this system. The charge Here the charge in the potential energy depend only upon the endpoints and independent on actual path. We can write this in this way. Here now we have calculate change in potential energy for a system of a charges. For system of 2 point charges q1 and q2 separated by distance r can be obtained from above equation by using r1 is equal to infinity and r2 is equal to r2 is equal to r, and q is equal to q1 and q0 is equal to q0 is equal to q2. Then energy, potential energy, this become u is equal to q1 upon q2 upon 4 pi epsilon naught into 1 upon r minus 1 upon infinity. Neglecting 1 upon infinity, we get u is equal to 1 upon 4 pi epsilon naught q1 upon q2 upon r. Then we discuss some unit of a potential energy. SI unit of a potential energy is joule. Symbolically we can denote it J, capital J, and full letters we can write joules. Other related units, 1 electron volt is equal to 1.6 into 10 raised to minus 90 joule. And next one, 1 milli electron volts, this become 1.6 into 10 raised to minus 22 joules. And then another units, 1 kilo electron volt, we can write 1.6 into 10 raised to minus 16 joule. In this way we can derive this relation. Then we can discuss define some term. Suppose potential difference, we consider 1 volts. Definition, we can prepare here a definition. 1 volt means the electric potential difference between 2 point is said to be 1 volt. The electric potential difference between 2 point is said to be 1 volt if 1 joule of a work is done in moving charge of a 1 coulomb from one point to the another point against the direction of electric field intensity. That is, we can write 1 volt is equal to 1 joule upon 1 coulombs. Then another concept we can discuss here. What is mean by 1 joules? 1 joule is the energy stored in a moving charge of a 1 coulomb through a potential difference is a 1 volts. What is mean by 1 joule energy stored? What is mean by 1 joule energy? 1 joule is a energy stored in a moving charge of a 1 coulomb through a potential difference is 1 volts. Then we can discuss what is mean by 1 electron volt. What is mean by 1 electron volt? 1 electron volt is a charge in the kinetic energy of a electron while crossing 2 point maintained at a potential energy of a 1 volt. 1 electron volt is the charge is the kinetic energy of an electron while crossing 2 point maintain a potential difference of a 1 volt. In this way we can discuss what is meant by 1 volt, what is meant by 1 joules, and what is meant by 1 electron volts. Next concept we consider here concept of a potential. From equation, potential energy can be written here u is equal to 1 upon 4 pi epsilon naught into q1 upon q2 upon r. We can write this equation q1 upon 4 pi epsilon naught into r into q2, and another way we can write this q2 upon 4 pi epsilon naught into r into q1. The quantity vr the quantity vr is equal to q upon 4 pi epsilon naught into r depend upon depend upon the charge q and location of point at a distance small r from it. This is defined as the electrostatic potential. In terms of potential, above equation can be written as potential energy of a two charges system. Then we can write here ur is equal to v1r into q1 is equal to v2. ur is equal to v1r into q1 is equal to v2 in v2r into q1, where v1r and v2r are the respective potential of charges q1 and q2 at a distance r from either. Then potential energy is equal to product of electric potential into charge. Potential energy denoted U, electric potential denoted V, and charge denoted Q. Then we can write this work done is this potential energy. We can write this work done is equal to electric potential and charge. Then W is equal to V into Q. Then V is equal to W upon Q. For system of two charges, we can write V is equal to W upon Q for system of two charges. Suppose first charge and second charge. First charge having potential V2 and second charge having potential V1. Uh, V1. Then we can write here for system of two charges V2 minus V1 is equal to dW upon Q. Work done, that is a charge in potential energy, change in potential energy per unit charge to move the charge from point second to point first. Okay, for system of two charges we can write v2 minus v1 is equal to dw upon q, means what? Work done, that is change in potential energy per unit charge to move the charge from point second to point first. Then we can derive a relation between electrical field and electrical potential. See this diagram, electric potential due to a point charge. Electrical potential due to a point charge. We can explain a relation between electrical fields and electrical potential. Okay. Consider a point charge. Consider a point charge plus q at O. The point capital M and capital N are separated small distance. Suppose this small distance we consider dx. Placed test charge q0 be the place at M. This q0 be the test charge place at point capital M when it is displaced from capital M to N. Capital M to N in this way. That time small work is done and it is given by, we can write this dw is equal to minus f into dx. Consider equation first. Here a negative sign indicates that force and displacement are opposite direction. By definition, we can write this E is equal to F upon Q0. We can calculate F, that is force. This force we can write F is equal to E into Q0. Then equation first becomes dW is equal to minus E into Q0 into dx. We can find dW upon Q0. Rearranging this equation, we can write this dW upon Q0 is equal to minus E into dx. But dW upon Q0 is a dV. Then dV is equal to minus E into dx. Here dV is equal to dW upon Q0. Therefore, we can write, we calculate E, electric intensity. This E is equal to minus dV upon dx. Here consider equation second. Thus the electric intensity at a point in an electrical field is the negative potential gradient at that points. This E is equal to minus dV upon dx. Consider equation number second. This gives the electric intensity at point in an electrical field is the negative potential gradient at that points. Then we discuss another concept is a zero potential. Another concept is zero potential. Some question asks this point, write note on zero potential. Write note on zero potential. The nature of potential is such that its 0 point is arbitrary. This does not mean that the choice of 0 point is significant. Once the 0 point is set, then every potential is measured with respect to that reference. The zero potential is set conveniently. In case of point charge, the 0 point is set as infinity. For a electrical circuit, the earth taken to be at zero potential. In this way, we can discuss these all terms. Firstly, we can discuss here what is mean by electrical potential, and we can derive equation potential energy. Firstly, we discuss what is mean by electrostatic potential energy. Then we can derive expression for potential energy. This expression become du is equal to q upon q0, q into q0 upon 4 pi epsilon naught into 1 upon r2 minus 1 upon r1. Okay, then we can discuss unit of potential energy, then concept of potential energy, and finally we can discuss the relation between electrical field and electrical potential, and last point we can discuss zero potential. In this way we can complete second parts in electrostatics. Today we stop here. Thank you.